This is the explanation for an experiment called Hall effect. So basically this is a phenomenon that happens when you pass current through a crystal. Here we have taken a semiconducting crystal in our experiment. So this here is a chip that has a semiconducting crystal. That crystal is represented here as a cuboid. And what happens is when you pass current through it, it's like having an electric field opposite to the flow of positive charge, right? Opposite to the flow of current. So when I have an electric field and magnetic field that are perpendicular to each other, we know that from Lorentz force has two components, Q into V cross P plus Q into E. So when a charge passes through an electric field and a magnetic field, it experiences a force. Similarly, as we see, conduction of current is nothing but flow of electrons. So when an electron flows, if the current is being conducted like this, electron flows in the opposite direction, right? So if the electron is flowing like this, and if there's a perpendicular magnetic field and if there's an electric field, there will be a force that's perpendicular to both these directions. Okay. So basically, if the electric field is along x-axis, if the magnetic field is along z-axis, my force, Lorentz force, the magnetic field component of the Lorentz force will be along y-axis. So because of this force, what happens is the electrons that are traveling, they come to one end of the semiconductor. Okay. That is, let's say they come to the bottom end of the semiconductor. So, which means that there will be equal amount of positive charge that's being deposited on the other end. Why does that happen? Because of deficiency of electrons, right? So, because of this, there's a perpendicular voltage, right? There's a voltage that's perpendicular to the flow of current. Now, this voltage is called as Hall voltage, and in this experiment, that's what we're measuring. Okay. So, if you see the apparatus here, we have 3 meters, 3 boxes. And we have a funny looking instrument here, and we have 2 probes. Okay, so this instrument here is an electromagnet, and as you can see, this electromagnet is connected to this power supply. So when you change the current, as you can see, this is current, right? So when you change the current here, the current that is being supplied to the electromagnet changes. Hence, the magnetic field. Where is the magnetic field? The magnetic field is in this region, in between these 2 rods, right? The magnetic field there will increase. So what kind of magnetic field is it? It's almost a parallel field of magnetic field. Okay. So that field, magnetic field increases with respect to the current, right? So that's what the function of these 2 apparatus is. Now you can see that I have 2 probes here. One of my probe is connected to one meter. The other probe is connected to the other meter. So this probe is called as Hall probe. Okay. This is the probe in which our Hall effect happens. Okay. And this is a probe that we use to measure the magnetic field. Okay. So their respective meters are here. So as I said, this probe is connected to this. We use it to measure magnetic field. As you can see in this meter, it's measuring magnetic field in Tesla. Right. Right now there is no magnetic field because I have not kept it in any influence. There might be some residual magnetic field due to this electromagnet. That's why it's showing some very slight magnetic field. Okay. And for this experiment, we are going to measure magnetic field in Tesla. Right, you can see that it's in Gauss and Tesla. We are going to use a Tesla one. Okay, that is the use of this probe and this instrument to measure the magnetic field. Where are we going to measure it? We are going to put this probe here in that region and measure the magnetic field. Okay, in the first part of the experiment, we'll use this probe. In the second part of the experiment, in the same location, we'll place a Hall probe, and this Hall probe is connected to this meter. If you closely look at this meter, I have something called as Hall voltage. I have something called as probe current. Right. So when I press this, you can see that the light is swapping from Hall voltage to probe current. So when it's in Hall voltage, it is basically showing me my Hall voltage. So if you want to see what Hall voltage in terms of this is, basically there is a semiconductor that's connected here, that's kept here. So that the same semiconductor is here. Now you can see there are 4 terminals, right? So basically there are 4 or 5 wires here, and when I click on probe current, basically it's changing the current that's passing through the semiconductor. And when I click on Hall voltage, it is measuring what perpendicular Hall voltage is being developed in the semiconductor due to the Hall effect. Okay. So basically what we will be doing in this experiment is initially this experiment has 2 parts. So what we will be doing in the first part is we are going to keep this probe that's used to measure the magnetic field here. Okay, and you'll have to slowly open this, right? Do not open it until you start the experiment because this is a very, very delicate material. So it's very easy to bend. Okay, so you just keep it in this magnetic field. In the first part of the experiment, what we'll do is we'll change the current, okay, and we'll measure what the magnetic field is. Okay, you can see when I'm changing the current, the magnetic field is changing, right? So what I'll do is in the first part of my experiment, if you see, I have a table that says current through the electromagnet and the magnetic field. Basically, right now we are not using Hall probe at all. The Hall probe is not involved in the first part of the experiment. All we are doing is we are calibrating the magnetic field in that region to the respective current. Okay. Basically, what we want is we want a graph that shows me how the magnetic field in that region is changing with respect to the power that I'm supplying to the electromagnet. Okay, in the first part, there is no power being supplied to the Hall probe. Okay, it's just the electricity being supplied to the electromagnet. So what we'll do is we'll change this current in gradations of 0.3 milliamps. Okay, you see this is milliamp. That's very important. So initially, what I'll do is I'll take at 0 or I'll switch it off. When I switch it off, and I keep this probe here. When I keep this probe here, you can see whatever the magnetic field is, that magnetic field comes here. I can remove it once, so and I can place it back there. I can see this is my magnetic field at 0 milliampere. So why is there a magnetic field if the electromagnet is off? The electromagnet always has a residual magnetic field. Okay, so because there is some charge that's still present inside the magnetic field, and hence there is still a magnetic field that's present. Okay, in that region. So there will be a residual magnetic field. You can also call it zero error, but we are not going to use it. At around 0 milliampere, I still have some magnetic field. Now, when I switch this on, and change it in gradations of 0.3. Okay, 0.3. When I have 0.3, the respective magnetic field you will take, right? So what you do is you do this for 0 to 3, 0 milliampere to 3 milliampere in steps of 0.3 milliamperes, and you measure your respective magnetic field. Okay, this is the first table, and you just plot this table on a graph, right? You take the magnetic field in x-axis, and you take the current that's being supplied to the electromagnet in y-axis, and you plot a graph. Now, after you plot a graph, what you'll do is you draw lines at 0.5, 1, 1.5, 2, 2.5, 3, up until 3 of current, okay, on y-axis, and you extend the lines and you intersect it with the graph, and you measure the respective magnetic field at that particular current. You go to the next table, you write it here. So you write 0.5, 1, 1.5, 2, 2.5, 3. You write the respective magnetic fields here. Okay. So basically what we got is from the graph, we got what the magnetic field is for a particular current. Okay. So this gradation can be anything, but in this case we are taking 0.5, 1, 1.5. So you repeat it again, you write it twice. Okay. Now why are we writing the table twice? The first one is for when my probe current is 0.5 milliamperes. Second one is when my probe current is 1 milliampere. Now how will I change the probe current? Now first thing is you have to understand that you make two columns. In the first column you write this, You see it's exactly the same. After that what you do is you remove your probe that's used to measure the magnetic field. Now you take your Hall probe and keep it exactly in between. It should not touch any of the sides of the electromagnet, but you keep it exactly in between. Once you keep it exactly in between, what you can see is you can go to the meter and you can set the probe current, change it to probe current and set it to 0.5 milliamperes. You don't touch it, you just change it to Hall voltage. You're not going to touch this now. What I'll do is I'll change this in gradations of 0.5. Okay, I'm not changing my probe current, I'm changing my power supply to the magnetic field, power supply to the electromagnet. Now I'm changing it in gradations of 0.5, 1, 1.5. Okay, at 0.5, whatever it is, approximately 0.5, you measure the respective Hall voltage. Okay, now at 0.5, my Hall voltage is something, and again at 1 milliampere, my Hall voltage is some value, right? So I measure the Hall voltage, right? Now what I do is after that after my one set of experiments is done, after I change it from 0 to 3 volts, 3 milliampere, I bring it back to 0. Okay, I go back here, I change my probe current from 0.5 to 1 milliampere. Okay, my probe current. Okay, around 1 ampere. Now, after that, I'm again not going to touch this knob. I'm going to change to hall voltage. Again, the same drill. Okay, you change it from 0 to around 3. You change, you see that my hall voltage is also changing, right? 0 to 3. Now, what you do is, after you're done with all these 3 columns, what you do is, you remove your hall probe from that place. Okay, you set your probe current to 0.5. Now, this is not in the influence of any magnetic field. You set it to 0.5 and you'll get some hall voltage. This is your V off, okay, voltage, hall voltage offset. So at some probe current without any magnetic field, I'm still getting some hall voltage. So that is kind of an error. So that's my offset voltage. Now I'm going to write that offset voltage here, V off, and I'm going to write it here. It's not written here. And similarly, I'm going to write an offset voltage when my probe current is 1 milliampere. Okay. So it's around 1 milliampere. I'm going to see what my hall voltage is. I'm going to take that down. I'm going to write it here. Okay. So when I probe is 1 milliampere, my offset voltage is this much. When my I probe is 0.5 milliampere, my offset voltage is something. Now what I do is, I take my offset voltage, I subtract all these from my offset voltage. For example, here my offset voltage is 9 millivolts when my probe current was 1 milliampere. Basically this, when my probe current is 1 milliampere, this is around 9 volts. Okay. So this is for some other apparatus, so it will change. Now what I'll do is, from all these hall voltages, I'm going to subtract 9 volts. And whatever value I get, I'm going to write it here. Now that is my actual hall voltage. Okay. When I account for the residual voltage in the probe without any without any magnetic field. Now these voltages, right? I'm getting 2 graphs. What I'm going to do is, I'm going to plot these graphs. So on my x-axis, I'm going to have my magnetic field again similarly, and on my y-axis, I'm going to have my hall voltage. Okay. So I'll get 2 graphs: 1.0, 1 for 0.5 milliamperes, one for 1 milliampere. What are these currents? These are probe currents. Okay. And this is hall voltage. This is magnetic field. Hall voltage, magnetic field. Okay. Are 2 different probe currents. Now I'll get 2 graphs. Now what I do is, I take the slope of this graph. Okay. When I take a slope of this graph, what will I get? y2 minus 1 by x2 minus x1. I'll get hall voltage divided by magnetic field. Right? Hall voltage divided by magnetic field. I'm going to find that out for both the cases. Okay. So you take those 2 slopes. When you take those 2 slopes, you go and see, you'll get something called as N, that is density of charge carrier. What is our charge carrier here? It is electrons. Okay. Now I want to know, it's actually electrons and holes because of the semiconductor. I want to know the total density of charge carriers. What I'll do is, I will take my I probe current for in this graph. For the first case it's 0.5, for second case it's 1. So I probe is 0.5 here. You divide it by its slope. After you divide it by slope, you divide it by the charge, that is 1.6 into 10 power minus 19. And then you divide it by the thickness. Thickness is written here. Okay. And then for the second case, again I probe divided by whatever slope you get here, divided by E divided by thickness. Thickness will remain same. Now once you get N, okay, once you get N, you take the reciprocal of that and again divide it by E. Okay, then you'll get some value. That value is called as my Hall coefficient. Okay, that's what you have to finally find out in this experiment. Okay, see, the same calculation is done. After I get my slope, I'm substituting it in this equation. I'm getting my carrier density. Once I get my carrier density, I'm substituting in this equation. I'll get my Hall coefficient. So I'll get 2 of my Hall coefficients. I'm going to take the average, and the average value of Hall coefficient I'm going to write. Okay, this is the experiment.